So if the sinusoidal functions require arguments that are angles measured in either degrees or radians, how is it that we're using these trigonometric functions to represent quantities that vary as a function of time? For example, we know the sine of 30 degrees is 1/2, but what is the sine of 30 seconds? To us, that second question doesn't seem to make sense, but it does in terms of the electric power system. Time can be converted to an angle because in an oscillating system, time is cyclical. Where we are within a single oscillation in a given instant is important, not which oscillation we are in. The angle therefore can be thought of as specifying the fraction or multiple of a complete oscillation. Time as an angle therefore means time is a certain fraction of a whole. We don't care whether or not we are on the first or 50th oscillation. Instead, we're concerned with where in a single oscillation we are at a given instant, such as a third of the way through or a half of the way through. Therefore, we can convert time into an angle for oscillatory systems by considering the rate or speed at which the sinusoidal function repeats itself. As we know that one full oscillation of a sine or cosine wave takes 360 degrees or 2 pi radians. We can measure the speed in one of two ways, both based on the number of occurrences of a repeating event per unit times, either in terms of radians or in terms of complete cycles. These AC speed measurements are the angular frequency, given the symbol omega. And this measures the rate at which a sinusoidal quantity repeats in terms of radians per second. This can also be thought of as the rate of change of the function's argument. So how fast is the argument of the sinusoidal function changing? The ordinary frequency given the symbol F measures the rate at which sinusoidal quantity repeats in terms of cycles per second. Also called hertz. So what we're saying here is that we have an AC waveform. We have one complete cycle. The ordinary frequency measures how many of these cycles are repeated per second. The angular frequency measures how many radians are transversed in a single second. So here we show it in terms of degrees, but we could easily convert this, the x-axis over into units of radians, 360 being 2 pi radians, and then we could figure out, well, how many radians did it transverse? So in this relationship, we can see that angular frequency, omega, is just related to ordinary frequency by the quantity 2 pi, since one cycle is the same as 2 pi radians. So let's work an example of determining the frequency of a sine or cosine wave. A sine wave representing a voltage source completes 3 full cycles in 1/20th of a second. Find both the angular frequency and the ordinary frequency. So what we're going to do is we're just going to start by drawing the 3 full cycles of the AC waveform. I've got a graph here that's already done this for me, right? So I've got 3 full cycles. 1, 2, 3 full cycles of the AC waveform. The information for this problem told us that since 3 cycles takes 1/20th of a second, so that occurs at 1/20th of a second. We've got a periodic waveform. Each of these cycles therefore takes 1/60th of a second to complete, meaning that the waveform repeats itself in multiples of 1/60th of a second, i.e. this point here is going to be 1/60 of a second. What's this one going to be? Well, 1/30th, right? Or 2/60ths. This would be 3/60ths or a 20th, et cetera, et cetera, et cetera. The time that it takes the waveform to complete a single cycle is often just called the period. So in this case, 1/60th of a second is the period. It's given the capital letter T. So in this case, T, the time it takes for one period to complete, is 60 seconds. So what we can say is that one cycle is completed in 1/60th of a second, or 2 pi radians are transversed in 1/60th of a second, or alternatively, 360 degrees are transversed in 1/60th of a second, right? All of those statements I've just made mean exactly the same thing. So now we can calculate the ordinary frequency by finding the number of full cycles completed in a single second. Mathematically, that can be written as the ordinary frequency is equal to 1 over the period, right? So that's one cycle, or 1 divided by the period, which is 1 over 60 seconds. So that becomes 60 per second. And so F is 60 hertz. Alternatively, we could have calculated this value using 3 cycles in 1/20th of a second. We could have said that F is equal to 3 cycles and that 3 cycles, remember, we took 1/20th of a second, 1 over 20 seconds. And so again, F here, we bring the 20 to the numerator, 3 times 20 is 60. We get 60 cycles per second, or 60 hertz, right? So it's periodic. Every cycle takes 1/60th of a second to infinity. That's what we mean by the term periodic. We can now calculate the angular frequency by finding the number of radian cycles completed in 1 full second, recalling that a full cycle is equivalent to 2 pi radians of angular rotation. So here we've got omega, angular frequency, is equal to 3 cycles times 2 pi radians in a single cycle and then we divide that by the total amount of time that it took, 1 over 20 seconds. And what do we end up with? 120 pi radians per second. Which is about 377 rad per second. From these calculations, we see pretty easily that the standard relationship between angular frequency and ordinary frequency, and I'll just tell you, most of the time we drop the term ordinary. We just say omega is angular frequency is equal to 2 pi times frequency. Although technically that's the ordinary frequency, most of the time we just drop that off. This example illustrates the conversion of time into an angle via the multiplication of the angular frequency. So if we multiply angular frequency omega times the amount of time, t, we get how many angles a sine or cosine has been rotating through. So that's how we can use sine or cosine to represent things that change cyclically in time, is because the argument is given in 2 parts. Focusing on the cosine function, we've got the cosine of theta, right? So here we've got cosine. We're taking an argument that this thing has to be in terms of either radians or degrees, right? It's an angle. But if we write this as cosine of omega t equals cosine of 2 pi ft, we retain inside the operator, we retain a argument that is an angle, but you see we do have 2 arguments inside of that. We've got either the radian frequency or the frequency times 2 pi, and then we multiply it by the time in both cases. And that's how we convert time into an angle for cyclical systems.